Well, let's get started and look at Gauss' law again. We're going to look at two examples today, two examples where we do not have uniform charge density. And these examples tend to be a little bit more involved, particularly because finding charge inside is not as straightforward as doing density times volume. An integral is going to be involved to find the charge inside. Okay, so we're going to work through these two examples that I have planned. But just as a reminder, I'm going to go over Gauss' law again because we need that repetition. We need to know what we're doing with flux, what we're doing charge inside. So with flux, we're looking at, we're just doing EA. Again, that matches, that you could do that if your Gaussian surface matches the symmetry of the problem, right? Matches the symmetry of the electric field, and then you have electric field that's parallel to your electric field is perpendicular, I should say, to the surface, and is constant around the surface. So if those two conditions are met, we could say flux is just EA, and the A here is always, the area of the surface area, I should say. So the surface area of the Gaussian surface. Okay, and then we get charge inside. Now, charge inside in the past examples, in the past video, the way we found charge inside. Let me do that in black. The way we found charge inside, so Qn, we just did density times volume. Okay, now that works great if you have constant density, because that density here is not changing, right? If you have uniform charge density, this value here is not changing throughout your whole volume. Okay, so you could just do density times volume. But if this is changing throughout your whole volume, we're gonna have to do an integral here, integral rho dV. And I talked about that in a previous video. Okay, now that dV, it depends on what you're looking at. For example, a sphere, when we looked at a sphere, dV, assuming that it's spherically symmetric, that it doesn't change at different angles, that we could say dV is 4 pi r squared dr. Okay, so this was for a sphere. Okay, for a cylinder, I'm going to hold off on doing the dV for a cylinder, because a cylinder, you could have something that changes as a function of length, that charge density changes when you go from, let me just draw a cylinder here and show you what I mean. So if you have a cylinder, and let's say charge density was changing like this. Okay, so the further you went this way, the more charge density you have. In that case, your dV is going to be a different function than, let's say, this scenario. Let me erase all this, where the charge density changed from the radius. I'm not doing a good job here. Okay, so that essentially it was 0, just for an example, it was 0 charge density in the middle, and as you went out, charge density increases. So those two situations will require a different V. You still start with a volume for a cylinder, pi r squared L. But to get dV, you're going to, or let me put it pi r squared Z here. Okay, where Z would be this distance. Okay, so if we're trying to find dV, if the charge is changing as a function of radius, then you do dV dr, which is 2 pi r Z. But if the charge is changing as a function of Z, which was my first example, when charge is changing along this direction, then you would do dV over dr. Oh, not dr. It was changing as a function of length. You do dz, which is pi r squared. Okay, so you kind of get two different dVs here, depending on what variable is density dependent on. If density is dependent on radius, you get 2 pi r z. If density is dependent on the z-axis, the axis of the cylinder, then you just get pi r squared for dv dz. Okay, and then you solve for dv. Okay, and you'll plug it in back here. Okay, so when we're dealing with non-constant charge density, how you take this integral is going to become really important, particularly what you plug in for dv, and of course what are you going to use for your limits, right? For your lower and upper limits. All right, so that's what we're diving into today, and it still goes back to this, right? We're still going to find electric field, so we still need to find flux, that's EA. We still need to find charge inside, that's this integral, and then once we do that, then we get our answer, right? We solve for E. Okay, so let's look at our first example. All right, so we did this example earlier, and, so I wanted to look at it again, but this time we're going to find electric field. So we have a sphere of charge, radius r. So here's my charge. Has a volume charge density given by the function alpha r squared. So this is a non-constant charge density, right? The charge density in the middle would be 0, and as you go outwards, your charge density is going to be increasing. All right, so more and more charge per unit volume as you come out towards the surface. All right, so in that scenario, what is the electric field everywhere? And remember, in the past video, I introduced the idea that we look at different regions. So what regions are we looking at here? Well, we have two regions here, inside the cylinder and outside. Okay, region 1 and region 2. So very similar to our approach from our example from the previous video, we separate this out into two problems. Region 1, which is when lowercase r is less than uppercase r. And of course, the lowercase r, I am referring to my Gaussian surface. Okay, so let's look at region 1 first, and then I'll look at region 2 afterwards. Okay, so region 1, when r is less than capital R. So I'm going to draw my Gaussian surface. Let's see, something like this. And remember the radius for our Gaussian surface, I'm going to say that's lowercase r. All right. Okay, so now I'm going to use that, now that I have my Gaussian surface here, I'm going to use that to get my Gauss's law. So let me write out Gauss's law. So Gauss's law says that my flux through my Gaussian surface, through my green circle there, equals the charge inside my green circle, or inside is really a sphere, right? So it looks, I drew it as a circle, but it's really representing a sphere. Charge inside that sphere, inside my Gaussian surface, divided by epsilon 0. Okay, so flux is easy. Flux is just EA. So I'm going to put that for flux, EA. And again, that area is the area of your Gaussian surface, lowercase r there. How about charge inside? Well, charge inside, let me bring out the epsilon 0 there. Charge inside, because you have a non-constant or non-uniform charge density, we're going to have to integrate to find charge inside, rho dv. And we did this function earlier in a previous video. So you can go back to that video and see what we did there. I'm still going to do it here, but I will do it a little bit faster than I did in the first video. All right, so we have EA equals, all that 1 over epsilon 0, again, or times my integral. Again, this is just from plugging in here. I plugged in for flux, EA, plugged in charge inside with this integral. And that's what I talked about back here. Qn equals that integral. Okay, so I have my integral, and let's plug in for A. So EA, well, the area of my Gaussian surface, which is a sphere in this case, 4 pi r squared, and 1 over epsilon 0, and then here's my charge density. Charge density is alpha r squared, and dV, since we're talking about a sphere, is going to be 4 pi r squared dr. Okay, so let's you know what? Let me take out all my constants here. So if I take out my constants, I have a 4 pi alpha that comes out divided by epsilon 0 integral. See integral. What is in there? R to the 4. Okay, r4 dr. and my limits of integration. What are my limits of integration? Well, I'm looking for charge inside this, my green circle. So I'm gonna start from the center and go all the way out to my lowercase r. That's my limits. 0, uppercase r. Okay, and of course the left side of my equation, I still have my 4 pi r squared. Okay, so let's solve for this. So my integral gives me r5 over 5, and then the r squared is going to bring that to an r cubed. So I'm just doing all the algebra here. Let's see, a couple things do cancel out here. The 4 pi's, right? They cancel out. So this 4 pi cancels out with that 4 pi, and I'm left with my electric field. Whoops, see, it's in black here. My electric field equals, let's see, I just want to make sure I don't make alpha r cubed over 5 epsilon 0. All right, let me just take a moment to make sure I did that correctly. I believe I did. R5 gets canceled with the r squared, so I get r cubed. And then, yeah, I get a 5 in the denominator because of the integration. All right, you could, if you work that out, you should get the same thing. So if you want to press pause on the video and do the calculus, right, evaluate that integral here, and then do the algebra to solve for E, you should get this. Okay, so again, this is our electric field when R is less than capital R, right? That's the only time we have this electric field. Okay, and if I wanted to, I could make this a vector r hat. All right, now let's look at region 2. Okay, so let me give you a warning here before I get into region 2. Region 2 is not going to be this. So electric field for region 2 is not going to be alpha capital R cubed 5 epsilon 0. I see that so often that when you go into a different region, what I see there is like, students will just think, well, all we're doing is replacing the limit, right? This lowercase r becomes capital R, so then all I need to do is replace this with capital R. Okay, that is not correct. There's a big mistake with that, and I'll show you in a second. So this is not the right answer. Don't do that. Okay, so let me erase that. Okay, so what are we doing for region 2? So region 2, which I'll work out in this page here. So we're going to look at region 2. Okay. And region 2 is when capital R is less than lowercase r. So I'm going to make my Gaussian surface now larger. It's almost the same size. There you go. Okay, so there's my lowercase r is now larger than my capital R. And so we're looking in that region, and I want to find, my question is, what's the electric field in this region? So what's my electric field here, right? Which would be the same electric field, same magnitude as the electric field here, or anywhere on this line. Okay, so I want to find the electric field in region 2. So I'm going to start from scratch. Well, yeah, I'll start from scratch, just so you can see what goes on. So charge or flux equals Qn over epsilon 0. Okay, so flux is still the same, EA. And charge inside is essentially the same thing as what we got earlier, right? If you go back to our integral here, what really changes when I'm now over here? Well, here's my charge inside. I still have the same function for charge density, same function, right? And I still have dV for a sphere, right? 4 pi r squared dr. So all this here is the same. My what is that called? My integrand is the same. What's going to be different now in region 2 is my limits, right? Where if I want to find charge inside my green circle now, my Gaussian surface, which is larger than the actual charge itself. What are my limits of integration? Well, it's going to go from 0 to r. I talked about this in the previous video that you do not include this space here because this space is all empty space, right? There's no charge in here. So you don't want charge inside, right? In your limits for your charge inside to go past this point here. Okay, so our limits essentially is the same integral, but our limits is just different. It's from 0 to r, which means this whole side is the same, right? So let me just copy this side, but I'm changing my integral. So we have 4 pi alpha, whoops, over 5 epsilon 0. Wait, was there a 5 there in the integral? Oh no, why don't you do this? There. Okay, so all this that we did here in the previous slide for Q inside, rho dV, plug in for rho, plug in for dV, simplify, right? Take out the constants outside the integral. Is the same thing. All we're doing is that we're replacing this with lowercase r. Sorry, uppercase r, right? The radius of the charge. Okay, so that's what I did here. Now, remember, A is always the the area of your Gaussian surface. So that A is still 4 pi r squared. Okay, and then we have 4 pi alpha. This becomes r to the 5th, right, after you take the integral over 5 epsilon 0. Okay, so I evaluated the integral there and we get capital R to the 5th power. And let me cancel out the 4 pi so that they go away. 4 pi here, 4 pi there. And let's solve for E. So, okay, oops. So E equals alpha R to the 5th over, well, it's just 5 epsilon 0 r squared. Okay, so this is my electric field for region 2. And of course we can make this a vector, right, just by adding the r hat. Okay, it's a positive charge, so it'll be going the electric field will be going away from the charge, right? If it was a negative charge, you know, the problem indicated that somehow all we would do is put a negative there, and we'd be fine. Okay, so here's my electric field. Very different, right? It's not the same electric field as we got here. This is for region 1. Inside my electric field, this is for region 2, outside my electric field. Okay, and together they give me the electric field everywhere in this problem. Right, so if I do a little axis here, and I'm going to draw a line for the, so this is a radius, capital R. Okay, so the inside, it increases as r cubed. Make that cubed a little bit closer. Okay, so we get an r cubed curve there, which might look something like this. Okay, and then after that, once you go outside, you know, this r here is the radius of the charge. Once you go outside the charge, it starts to drop as 1 over r squared. All right, something like that. And so this is my electric field here, and this is my distance from the center. All right, and that 1 over r squared, right, very similar to a point charge. So what happens afterwards is that this, you know, I could show you, it'll take some work, but I could show you that this would be equivalent, this would equal kq over r squared, where q is the total charge inside of my sphere. All right, you could probably show that. You could probably go from this to this, just by, you would have to find out what is qn and do some algebra there, but you would get this equation. So once you go outside the sphere, this electric field is just the electric field for a point charge. Really kind of interesting there, that it doesn't really matter that once you get outside, that is, once you get outside the surface, it doesn't really matter that you have all this charge density here. It just, essentially from your perspective, from if you're just measuring the electric field, that electric field would be no different if you just had a point charge at the center with the same amount of charge as this sphere. Okay, I hope that makes sense. So if you replace this charge with just 1 point charge at the center, but it still has the same total amount of charge, the electric field over here will be the same, whether you're looking at a sphere or whether you're looking at a point charge. Okay, so that's what we see there. All right, so you can kind of see where the difficulty comes in these kind of problems. It comes from finding charge inside, right? It's evaluating this integral. The flux is pretty much the same as our previous problems, just EA, and you just got to plug in the right area there. But it is that integral that you have to be really careful with. All right, let's do our next problem, which is a little bit harder. This one I actually took from your textbook. It is, I don't remember what section it is. Actually, I have it right here. What section is this? 24.6 in your textbook. Okay, so I thought it was a really good example, so I wanted to do it with you guys and show you what would be the approach to this. But your textbook has a solution there anyway, but I think it'll still be helpful for you to see me do this. Okay, so let's look at this. So we have a infinite slab of thickness 2a. So this infinite slab is kind of like a plane of charge, but usually in the past, our plane of charge has just been this two-dimensional sheet. Now I'm saying it's kind of the same thing, but now I'm giving it a thickness, right? So it's infinite in the sense that it goes forever this way, goes forever this way, it goes forever outside the screen, goes forever inside the screen. Okay, obviously limited in the z-axis, so it stops here and it stops there, but it's infinite in all of the directions. Okay, so if I put that in terms of the axes, it's infinite in the x-axis and is infinite in the y-axis. Okay, it is not infinite in the z-axis. Okay, so this infinite slab of thickness 2a, so that's my thickness of my slab, has a charge density that changes along the vertical axis of the slab. So it changes as a function of z here. And the charge density is given to us by the function here. So charge density is a function of z equals rho 0, 1 minus the absolute value of z over a. So that absolute value is essentially telling us that this charge is symmetric. What's the wording there? Charge is symmetric along this axis here. Okay, so whatever's happening to the charge on top. So let's see, 1 minus z. So as z approaches a, it's going to go to 0. So you have a large charge here, but then goes to 0. Well, same thing on the other side. All right, so it's symmetric. What happens on top of this axis is the same thing that happens below this axis. All right. Okay, so let me add a couple more things here. Let's see, infinite slab of thickness 2a. So the total thickness is 2a. So that's this thickness. Okay, so I'll call that 2a. That means that this position here, I'm going to say positive a, and this position here is negative a along my z-axis. Okay, so the slab goes up to positive a, and it goes down to negative a, and that gives me my 2a thickness. Okay, let me see, what else could I do here? I think that's it for now, as far as setting up the picture. All right, let's go to the question. What is the electric field everywhere? Okay, so once we draw the picture, we got to ask ourselves, what regions are we looking at? What are the different regions that electric field is going to have a different function? And those regions in this example are just inside the slab, which I'll call region 1, and outside the slab, which is region 2. Okay, so we're going to find the electric field in region 1. What would be an appropriate Gaussian surface here? Something that has a symmetry of a slab. Okay, there's a couple of options, and it doesn't really matter because you get the same thing at the end. You could pick a cylinder. Right, that has that symmetry, or you could pick a cube. Well, not a cube, but like a box kind of thing, because it's not equal on all sizes. Okay, so either way, it doesn't matter which one. I think I'm going to stick with the cylinder only because it's easier to draw. but either one has the same symmetry. If you think about what the electric field is doing, okay, well, the electric field for a slab, especially since we're talking about infinite slab in the x and y axis, because this is an infinite slab, our electric fields will only be going in the z direction. So electric fields will only be looking like this. On the outside, you have electric field, oops, looking something like that. Okay, so it is only in one direction along the z-axis. So either one, this or this one, because our conditions are met, that for this cylinder or for this box, that your electric field is perpendicular to your surface, okay? And the electric field will be constant along the surface, here and here, same thing here. Electric field is constant here and constant there. So either one matches our conditions that we need for a Gaussian surface, right? To have electric field perpendicular to the surface and having electric field to be constant along the surface. So it all matches there. So we're either one. So I'm gonna pick the cylinder here. So let me erase this. Okay. So there's my cylinder, and I'm gonna pick. Let's see, what would be a good dimension here? Let me do this. I'm gonna call this. Well, I don't think the radius matters. Let me just say the height. Oops. Okay, so I'm gonna call that distance z. And of course, going the other way would be negative z. So that height there of my cylinder is all measured based off the axis there. I don't know, we call it the x-axis if you want. Okay, so z above the x-axis, z below the x-axis, right? And I guess the y would be going into the page there. Okay, so let's find, so here's our Gaussian surface. Let's find the electric field in region 1. Okay, so region 1, what do I mean by region 1? I'm talking about when z, the height of my cylinder, is less than a. Okay, so we're looking when we're our z is less than a there. So we're not, our Gaussian surface is not passing this boundary, right? It's not going above it. It's just staying within it here. Okay, so where do we start? Well, kind of the same thing as we've been doing. Let's just start with Gauss's law. Flux equals EA. Flux equals charge inside over epsilon 0. Okay, so this one's definitely a little bit more involved because when I say flux is still EA. I'm going to talk about charge inside in a second. Okay, but what area are we talking about here? Okay, we have electric field coming out of the surface here, electric field coming out of the surface here. So definitely this area and this area, both of these surfaces, the top end, this is my soda can, the top of my soda can and the bottom of my soda can, both of them have flux going through it. And both of them have positive flux. Right? Remember how we say positive flux. Positive flux is when electric field goes out of your surface. The electric field is coming out, electric field is coming out. Just because this one's going down doesn't mean it's negative flux, okay? Electric field is coming out of it, so we take that to be a positive flux. Positive flux going down, positive flux going up. Do I have any electric field going like this? Let me show you. Like that. Electric field going through the edges. And the answer to that is no. Okay, you don't have any electric field going through the edges. In other words, you're not going to have an electric field have an X or Y component. How do I know that? Well, because it's infinite in that direction. If there's a charge causing an electric field to go this way, then there's going to be another charge causing an electric field to go that way, right? And so the X and Y components will always cancel. Okay. So no electric field going through the edges, going through the sides of my can, only to the top and only to the bottom. So as far as my area here, as far as calculating my flux, this area needs to include the area for the top and the area for the bottom. So I'm going to write this as E2A, where A is the area on the top here, and A is the area on the bottom. Now I could have defined this, I could have defined some radius here and some radius here and plugged in pi r squared, but, and feel free to do that. If it makes sense to you to define a radius here, then do that. My suspicion is that this area is going to get canceled out, only because of what I talked about in the beginning of this lecture. That, go back here, we're going to have something like this. So let me explain this. Let's explain that. Okay, so we know this is going to equal charge inside over epsilon 0. Okay, let me take a break from this and just look at finding charge inside. How do I get charge inside here? Because we haven't done this, we haven't done charge inside for this problem. So we're still going to start out rho dV. Okay, and notice that my volume or my charge density changes as a function of z, right? Changes in the vertical direction here. Okay, so if I have my volume, the volume of my Gaussian surface will look like this. Volume of Gaussian surface would be pi r squared times z. Okay, if I want to get dV, but my charge density is changing as a function of z, I need to take the derivative of this as with respect to z, because that's how my charge density changes, right? Because eventually I'm going to do rho dV, right? So I need to make sure that this dV is taking into account that this charge density is dependent on the z-axis. So if I do dV dz here, for that reason, the reason being that the charge density is dependent upon z, I get pi r squared, and dV equals pi r squared dz. Well, what's pi r squared? This pi r squared here is just the area of this. So I could just replace that with just a dz. A dz. Okay, so charge inside equals my density, and then for dV, I'm going to plug in a dz, where again, a is the area of the top circle and the bottom circle, of the top end of my soda can and the bottom end of my soda can. All right, so now we're going to get density. Let me plug in my equation for density. Now, density is symmetric, right? Whatever charge is on the top half of this, can of my cylinder is the same amount of charge on the bottom half. Okay, so if I just focus on the top half, get the charge, how much charge is on the top half, I could just multiply that by 2, and then I get the charge total. Okay, so I'll explain that one more time. Because of the symmetry here of my charge, right, given to me by this absolute value, however much charge I have in the top part of my cylinder will be equal to the charge in the bottom part of my cylinder. So my idea is that I would just calculate how much charge I have in the top part and just multiply that by 2. So it'll be 2 times 0 to z. So that's the limits from my top, right? The top part of my cylinder from 0 to z. 0 to z. Okay, so 0 to z is just the top, and I'm multiplying it by 2 to get the total. And I get, what's my equation? So charge density is rho 0, 1 minus z over a dz. Okay, so I factor out. Oh, well, I guess I don't have to put the absolute values here since I'm only going from 0 to z. So I could just keep this as z. All right, so what do I get there? I don't know if I could do this in one shot. Qn equals So the a comes out. So I'm going to put 2a and get essentially two integrals I have to evaluate. 0 to z, rho 0 dz. Oh no, I could factor out rho 0, I guess, too, huh? That's another constant, rho 0. Yeah, I mean, I didn't mention that earlier. This rho 0 here is just some constant, some initial charge, some factor to multiply the rest of this by. So it's just a constant, just a number. Also, let me just say one more thing before I go on here. For some reason, students look at this and think that it's a given equation for other problems. This equation here for discharge density is specific to this problem. Right? You will not see this charge density in another problem. Okay, so we're just using this as an example to see how do we find Q inside, or how do I find electric field for this example. Okay, so don't write this down on your note card and think that you'll use it for an exam. Okay, don't do that. You will not. Okay, so let me see. So to factor out my rho 0, where was I? So I'm going to find the integral from 0 to z, and that's just going to be dz minus integral 0 to z, and that's going to be z over a dz. Okay, so I need to get that integral. Okay, so Qn, let's see, would be 2a rho 0, and then after I do my integrals here, let's see, so my first integral, integral dz, well, this gives me z, right? So z. And then on the other integral, so z over a dz gives me z squared over 2a, right? So it's going to be a minus z squared over 2a. Okay, so this is my charge inside my Gaussian surface. This Gaussian surface here. Okay. Definitely more involved than our previous examples, because you have to be careful about that symmetry, right? That's why I have this too. Because this whole thing here, this integral is just the charge inside the top half. So if I want the charge inside my whole thing, which is what Gauss's law tells me to find, right? If I want my charge inside the whole cylinder, I need to multiply this by 2. 2 times the top half gives me my total charge. Okay, so I think I did everything there right. So let me, let's go back here and go back to Gauss's law. So Gauss's law we left with is E2A equals, and then I have my charge inside 2A rho 0 over epsilon 0 times z minus z squared over 2a. All right, and then divided by 2a there. So the 2a's cancel out. And this is what I said earlier. It doesn't matter that you did a cylinder. It wouldn't matter that you did that box, because this area goes away. So it'll be the area of a square if you did a box, or the area of a circle, right, for the cylinder. So that goes away, and here's our electric field. So our electric field is now rho 0 over epsilon 0, and then I have my function here, z. I guess I could factor out z there if I wanted to. Z squared over 2a. Okay. The only difference here is you can't get a piecewise function because for positive z, this would be pointing in the up direction. For negative z, this would be pointing downward. So, I guess I would write like this. Negative rho 0, oh no, positive. If I want to be particular about my direction, that's all. So rho 0 over epsilon 0, z minus z squared over a. This is for z greater than 0. And you should do the same thing, but it'd be negative. Negative rho 0, epsilon 0. Z minus Z squared. All right. Okay. For Z less than 0. I think that should work out. Okay, I think I put the opposite because I was just thinking about this. This will still give you, I don't want negative numbers essentially. So I should have put the opposite value here. So let me just fix that really quick. It's not a huge point. Just trying to capture that symmetry in my equation. Okay, and this would be k hat. K hat. Okay, so the point is that electric field is symmetric. Whatever value you get for your electric field in the positive Z is the same value you're going to get in the negative Z. They're just pointing opposite direction. So I'm talking about this. So this value for electric field will be exactly the same as this value for the electric field, but one would be going up, one would be going down. Okay. All right, that's region 1. Region 2 will go by a little faster because we have our equation for our charge, right, which is this. So we're going to use this again for region 2. So region 2, which in region 2, I'm going to look for my Gaussian surface when Z is now greater than A. So let me show you what I mean there. I'm going to have a new Gaussian surface for region 2. So I'm going to have a cylinder up here, and this is going to go down like this. Okay, so kind of the same idea where the height, this height here, I'll call Z, and that's now greater than A, right? It goes beyond beyond this point here. Okay, so we still have the same electric field. Electric field is still going in the Z direction. So we have electric field going like this, electric field going like this. All right, so everything's almost the same, right? For region 2, I'm going to start with Gauss's law. We're going to do this. I'm going to do this, right? I have 2 areas where flux is coming out, where we have positive flux, the bottom and the top. So we're still going to have the 2A. Everything is the same about charge inside. You know, you work through this whole thing, we still have the same charge density. Now, the only difference is our limits. What is our limit? Where does charge stop as I go from 0 up towards Z? Well, charge stops right here. Right? I don't have any charge here. All this charge past this black line is 0. Right? There's no charge density up here. All my charge is down here. Okay, and I have charge down here as well. It's symmetric. So I could do the same trick where you do 2 times this charge density here, or this region. Okay, so it'll be the same thing. All I'm doing is replacing my upper limit with A. Okay, so I'm only going to integrate, oops, up to A here, to that point. Compose A. Okay, so what that would leave me for my Q inside. Do Q inside over here. So Q inside for region 2 is 2 capital A rho 0. Right, all I'm doing is looking at the same equations I had here. I'm just going to put, instead of Z here, I'm going to put A. A minus A squared over epsilon 0. No, over 2A. Where'd that epsilon 0 come from? Okay, so Q inside will always be a positive value there. Okay, so I guess I could factor out the A as well. Oh, actually, yeah, I do. I can, huh? So 2a rho 0, factor out the a, and I get 1 minus, what would that be, a over 2? No, the a's cancel, it's just 1/2. Look at that, look at that. Okay, simplify this way more than I thought. Yeah, factor out the a, yeah, I just get 1/2. So this just becomes q inside. This is after some algebra here. I get this. Okay, so let's go back to Gauss's law. I guess I could just start Gauss's law over again. So flux equals charge inside over epsilon 0. And of course, we're talking about this volume here, or this Gaussian surface right here. Okay, so my flux is from the top and the bottom. So I'm going to get a 2a there. So flux is E times A, but in this case 2a, because we have flux going from the top side and the bottom side. Qn is A rho 0 A over epsilon 0. And let's solve for E. So electric field for E equals, let's see, rows, so the A's cancel. This A and this A cancel. And I get, let's see, rho 0, whoops. Rho 0A over 2 epsilon 0. There you go. That's my electric field for the slab. Now, look at that electric field. What does it tell you? Does electric field get smaller once you get outside the surface here? So once you pass this slab, what happens to electric field according to this function? In other words, let me ask a more pointed question. Is this electric field dependent upon Z? Okay, no. All right, so what this is telling me is that electric field stays constant for an infinite slab. Well, that's pretty similar to what we saw earlier. For a infinite sheet, you know, we got this equation, right? 8 over 2 epsilon 0. Well, it's almost the same for an infinite slab. You just have charge density, volume charge density times the slab thickness, or half the slab thickness. Okay, so we get a constant electric field here. And of course, we can make that piecewise, just like we did here, where you get positive for Z greater than 0 and negative for Z less than 0. So we could have done the same thing I did here for this. Okay, but this just tells us the magnitude of electric field. Okay. All right, so that problem was probably the more involved problem, because there's a lot to consider there. But you know what is the same is, you know, our starting point, right? You always start with flux, charge inside, and you think about, okay, what's having the flux? Where is the electric field actually going through? And that one goes to the top part and to the bottom part. We had to be careful there because, you know, I don't think we've seen that before. So it's 2A, right? And then charge inside, that was the trickiest part, right? Finding how much charge is inside my Gaussian surface for region 1, or how much charge is inside this whole Gaussian surface for region 2. Of course, but for region 2, it's just this volume. Okay, and we went from there. Just did the integrals and did the algebra. All right, so we've done quite a few examples now finding electric field from Gauss's law. Again, using Gauss's law only really works if you have high symmetry, right? So a slab, a sphere, a cylinder, right? Those things have very high symmetry, and so Gauss's law is effective there. What we're going to do next in the next video is see how does Gauss's law affect conductors, or how can we use Gauss's law to understand conductors better. So we'll be doing that next time.